Hi Sven. So in our last video, we talked a little bit about the history that led to your decision to use interferometry for the Selene guides, how other options were ruled out, and what actually the background behind the solution is that you finally implemented. So then we had to cut the video off because it was getting quite long. And then what you still wanted to explain was a little bit the design history and the design reasonings of the metrology card itself, because that would be crucial for the effectiveness or for the performance of the whole system, correct?
That's right. So we identified that basically having this card on rails, even if you take the most precise Schneeberger rails or whatever you'd find on the market, we would be off with the tolerances. So basically those rails had to go, and we have to think about something else to actually make the measurement that is described here in different video possible. So we were looking into what is actually done with very precise machining, with very precise metrology systems. One thing that is used is basically having pressurized feet that are running on a granite surface, and then you pressurize the feet, they lift off a couple tenths of millimeter. You can move over the very well defined granite floor, so those can be machined within microns over meters, which is actually the precision that we need here. Yeah, and then you can let this pressurized foot down. You can make these things on top very rigid, so you have a very high repeatability if you do those lifts. Now our system is in vacuum, which makes pressurized air feed not very applicable. So we had to think about a different way of achieving the same effect. And what we did is we accepted that we're not going to have this measurement plate, if you will, on rails, but that we have to build a cart around it, something like this, and that we somehow have to make a mechanism that allows us to swing this measurement plate away from a reference surface that would be somewhat here and here, to move it along the carrier, and then to let it down, measure, and move it away again to drive. So that's what we went for. We just basically chose a little bit different setup for productability. So we made this card piece a little longer. We put the rails here on basically a horizontal surface, something like this. We had a tooth wheel here where we have the, basically like this, the motor. We have an energy chain here on top where all the cables go in, and we have a second rail down here. Then we created basically a setup where we have a flexure system, where if you want to, basically a metallic sheet is hung here and fixed, something like this, on the cart and on the measurement plate, and basically the measurement plate can now swing freely. Additionally, we have introduced a mechanism that is spring-loaded. So basically, when it's basically a puller that pulls the measurement plate back to a limit position, and that can also very smoothly and slowly release this measurement plate, and then the measurement plate is pressed against this with springs to again have a very reproducible pressure with which it is pressed on here. Additionally, we have made, then in the testing, we identified that the heat load from the motors is very significant to expansion of this whole system, and the motor, even with a very low temperature increase, we're very quickly off by multiple micrometers, which would be unacceptable. So we made a temperature lock, put the motor far away up here, made a temperature lock to isolate the system, and with that we finally achieved a system with a high repeatability. The only thing that we now had to achieve is to make this carrier very rigid and make the reference surfaces good enough and characterize them good enough. This can be done with interferometry and was done with interferometry. So basically what you do here is you have your precision surface, you take two mirrors, you take two collimators here, and you make two reflectors here, here and here. Those two reflectors are on a cart or on a sledge that is basically something like this, which has 2 feet which make contact. Here you come, when you come here, you can basically then again make an interferometry measurement between those two beam paths when you drive the sledge along this this line, and what you will see is not directly the deviation in basically if you would have a bump like this. What you would then see is if your cart moves down here, with the reflectors here and here, is that in the position here you get the same distances for both beams, and with this situation here you would get a distance offset between those two reflectors. That and the distance between the reflectors gives you the angular offset, and if you additionally have the absolute position of the reflector, you then also get the curviness of this surface. That's how the surfaces are measured, and that is also how one could potentially re-characterize those surfaces. So basically mounting two of these reflectors to this blue plate and running this along the guide would then allow you to re-characterize the surfaces, and with them re-characterizing the entire guide with interferometry.
Great. Thanks a lot for the great explanation, Sven. And I think in one of our next videos, we will have a look at the actual components, at the metrology card, and how what you described has been implemented in reality. Thanks a lot.
Thank you.